Hello and welcome to this SlimDevOps episode 50. These are a little bit different from previous live streams. It's going to be the start of a series where I'm going to be looking at how we can optimize an operating system to run on the Raspberry Pi that is purpose-built for running and building containers. So I think I'm going to do two today. This one a little delayed due to some building evacuation drills that have been taking place here, although they haven't happened yet. I'm told that they're not happening now, so if the alarms go off, I may not hear them. But I'm going to start this stream by going through building out an initial sort of tuned Ubuntu operating system for the Raspberry Pi. So if we just take a look here, this is my desk. This is my dev machine I'm going to be using here, and I'll explain why these are here in just a moment and how working on these sorts of devices has kind of inspired this idea. So let's just talk through what I'm hoping to do over, I'm not sure how many streams, but certainly a couple of today and maybe a couple next week to sort of round it out. But I'm seeing sort of more and more development, not just container related, targeting ARM, because you can now deploy to ARM in the cloud, and the Apple M1 and M2 Macs have also sort of seen a sharp interest in compatibility for containers on ARM and all the rest of it. And I don't have an M1 Mac. What if I want to make a container that I can share with a colleague who is on an M1 Mac? So I thought there's some fun to be had here. And looking at CI/CD pipelines, I see a lot of people bumping into issues with ARM related builds. So I haven't done much. I've done loads with the Raspberry Pi over the last, 8 years or so, but I haven't done much with using a Raspberry Pi to run and make containers. Although you'll see that I have use containers a lot in order to construct these operating systems. So what I'm going to try and do today is create a custom Ubuntu based operating system. So this is the host operating system that will go on the Raspberry Pi, and we're going to try and do a few things. We're going to try and see if we can get the memory footprint lower than the Ubuntu edition for the Raspberry Pi. So we're going to try and trim back some services that are persistent. And we're also going to try and trim back the disk footprint, although I don't think that that's going to represent a significant improvement. And then we're going to see what we can do to then, maybe not in this stream, but in subsequent streams, tune the Raspberry Pi bootloader configuration to try and preserve as much of the RAM for the operating system and the containers that it's eventually going to run, rather than things like the GPU. So this is going to be sort of a multi-tiered approach, and fits very nicely with what we do at Slim.AI, where we're all about making containers smaller, faster, more optimized, more secure. So this is just an expression of that, but we're really focusing on the Raspberry Pi, because in some cases the Raspberry Pi can be quite a small target to hit. So that's where the sort of the constraints start to matter. So if we just go back to the overhead view, I'll explain sort of where the inspiration for some of this came from. Hey Troy Borg, hey, welcome to this stream. I know I've seen you on my own channel before. Welcome to the stream. Slim down the server edition. It's the server edition that I'm going to be making my own Ubuntu based server edition. That's what I'm going to be working on there. And hey, Sandhaya, is that? I'm not quite sure on the pronunciation, but hello and welcome. So let me explain sort of what I've been working on. So I've been working on Raspberry Pi stuff for many years now, mostly going the other way as it happens, mostly trying to cram a fully fledged desktop operating system into a Raspberry Pi right from the early days when the Raspberry Pi 2 came out. I've been trying to do this, and I've had some success at that. So one of my hobby projects is Ubuntu Mate, an official flavour of Ubuntu. And I've been making versions of Ubuntu Mate for the Raspberry Pi since 2014, since that Raspberry Pi 2 came out. And I'm in the Raspberry Pi Insiders program, so I get engineering samples of early prototypes of new Raspberry Pi devices in order to work on that and do hardware enablement. And that carried over when I worked at Canonical, so I was previously at Canonical, and I sort of helped spearhead bringing the Ubuntu desktop, the full Ubuntu desktop, to the Raspberry Pi whilst I was there. So, you know, I've been messing around with Pi related stuff, and one of my hobby projects is these things at the moment. Making an operating system to run a retro gaming operating system for the Raspberry Pi. And when we start looking at these, this looks like a Game Boy, but it's like a reproduction case. And the Raspberry Pi is actually in the cartridge. In the case here, this is a Raspberry Pi Zero hiding inside there. And that's a small target to hit because of the RAM and CPU limitations. So I've had to tune an Ubuntu based operating system for this device. And again, you know, similarly, these are different cartridges that go in this device, and inside this one is a Compute Module 3. So that's another sort of embedded focused edition of the Raspberry Pi. And then this one's the Compute Module 4, hiding in this one here. And again, these are increasingly more powerful than this, but you've still got storage constraints, memory constraints, processor constraints, although they all relax a little bit as you go up the editions. So based on what I've learned making this retro operating system, which again is targeting and trying to get down as small as possible, it got me thinking about containers generally on the Raspberry Pi. So after I think I'll be successful in at least making a sort of a server edition of an operating system. I'm fairly comfortable that that's going to be successful. I think then the follow-on challenge will be, can I make optimized base images? So again, take Ubuntu and make optimized base images so that we can run those ARM base images on this operating system, again, to try and keep things as tight as possible. Because I did see some years ago, somebody managed to run, I think it was like 2,000 container instances on a Raspberry Pi. Oh, it was actually more than that, but it was around that number. I'd like to go back and revisit that and see what they actually did and see if maybe we can beat it. So I don't know if that will be possible. Now, I could fall on my face. I may find that when I get into optimizing my own operating system, that it's not any smaller than the images that Canonical provides. So we'll see how we go. Hey, Troy. So I'm just looking here. Let's just bring this up. So Troy says, I was using the Pi 4 with the Ubuntu server and then doing the Docker version of Home Assistant. Excellent. Okay, that's a great use case. And you had its data folder, I'm assuming this is the Home Assistant data folder, mounted as an NFS share to my NAS to save I/O on the SD card. So I am going to be doing this work on SD cards, but this particular case I've actually got an SSD connected to the USB bus, which is considerably faster than the micro SD cards. But things like the compute module, some of them have eMMC storage. It's not very big and it's not very fast, and they also do have SD cards. So I think what I'm going to do is mostly work with SD cards as sort of worst case example in terms of storage. Okay, well, I'm glad that this is a new topic for you. Santa? I'm sorry if I'm not pronouncing that correctly, but hopefully we'll learn something together. We're going to dig into some sort of the internals of Ubuntu and how Ubuntu is actually put together. And as I say, I used to work at Canonical. I was engineering director for Ubuntu for for a spell, so I have some experience in wrangling Ubuntu and doing interesting things with it, but I'll sort of explain what I'm doing as I go. And if anyone's got questions, or better yet suggestions as to what I'm doing right and what I'm doing wrong, then let me know. So I think what we'll do is, what I've done is I've got a script which builds my operating system for retro gaming. I've taken that and just done a copy, and I've gone through it and done a quick name change, thrown out all of the emulator stuff. So I've got sort of the skeleton of what I need to be working with. I'm going to open that up and we'll start, and we'll go into the bootstrapping stage and actually sort of try to create the initial file system, and then we'll progress through the extra bits, and we'll get like a basic OS working. So that's the plan. So let's take a look here. So this is my script. I hope that's visible enough. If it's not, I think there. Maybe that's a bit bigger and a bit more readable. We'll just get rid of this. So I'm calling this Slim.AI. A bit of a mouthful. If anyone's got better name suggestions, then let me know. Hey, Memo Twitch, thanks very much for the raid. I appreciate that. How was your stream? What were you working on? We're just about to start making a operating system for the Raspberry Pi based on Ubuntu, optimized for running containers, but right at the very beginning. And this is a sort of how hard could it be challenge. I've got an idea where to start, but I don't actually know if I'm going to be successful. So this is my script. We've just got a simple thing here to toggle which architecture we want to target. ARM-HF, which is 32-bit, or ARM64, which is 64-bit, obviously. At the moment, I'm going to ignore 32-bit. I'm just going to focus on the 64-bit stuff. It should be fine. I've got a helper function here. This is just for basically moving caches around. If you're familiar with Docker and layer caching, this is like a poor man's layer caching for the way my build script works. And then here's my helper function called nspawn. And this is using a different container technology to actually build my operating system. So nspawn is a wrapper for the systemd nspawn command, or systemd's container manager. So what we're using this for, this is just a wrapper around systemd nspawn to step inside a container managed by systemd in order that I can run arbitrary commands inside that container. So I'm running this build script on my, I see my camera's decided to focus on my friend behind me. I see, so I'm going to be running the build on my AMD desktop workstation. But what this is doing is using the systemd container and QEMU user static to do syscall translation for ARM. So when I step inside the container, it's an ARM container and it operates like an ARM computer, but with the power of my, workstation. So that's one of the things that I've been doing for some time now in order to sort of, accelerate the time it takes to build things. Hello, Solo Pietro. Welcome to the stream. Thanks for stopping by. Right, so this is, if we just look at the very bottom of the script, I have different stages outlined. We have a bootstrapping stage, create the base OS, then a bit where I'm going to install Docker. We'll play with this over time because I think we can add support for multiple container runtimes, because I know that's something that people will probably be wanting. Then we've got a stage here for installing all of the bits that the Raspberry Pi kernel requires, and I think there's some optimizations we can do here for this particular project. Then some configuration stuff. This is just a step I have in my regular scripts. We may not need that, or it may be very lightweight. Then a stage to clean up the file system. So because we've been stepping into the container and running a bunch of commands, there's some cruft that we need to hoover up. and then actually make the image itself and then compress it. We don't need to do the compression step. So let's have a look here. So Troy says, I don't think I've seen you ever do a full build. You usually only do the later stages. Yeah, when I'm doing these projects on my own streams, I usually get to around the point where the kernel has been done, because I'm usually just iterating on like integrations of particular bits. But we're going to start right at the top, right at the very beginning, and I'm going to try and explain what's going on in that bootstrapping stage, because this is where we really sort of set our stall out. So let's go and look at that function here. This is what we're going to run. So we install some stuff on the host, or make sure the necessary tools are installed on the host that we can run the build. And then this is where it gets interesting. You'll also notice these references to apt-cacher. Apt-cacher is what it sounds like. It's a caching proxy for apt packages, deb packages pulled in via apt. I'm running this on my build machine, and that's so that when I have repeated builds, it doesn't have to go out to the internet and download the packages each time. It's got a hot cache populated with all of the stuff. It just accelerates the process when we get into it. So we make sure the host is equipped with all the tools we need. And then I've just got some comments on some of the things that I'm going to be doing with the way that this is constructed. So if we have a look here, Deb Bootstrap is a tool to actually create an initial file system of a Debian-derived operating system. So this can work for Debian and Ubuntu and the other derivatives. So we're specifying the architecture we're going to target. So that will be one of the ARM architectures in this case. We're pointing at a cache directory. So what we're doing here is this bootstrapping process downloads a bunch of packages, and I'm going to cache those. So again, subsequent builds don't have to download all of that stuff a second time. We're then going to enable a bunch of components, and actually we made this that won't affect the performance, but this is basically everything that the Ubuntu archives make available. Maybe we don't need multiverse, but for the time being, I'll leave it enabled. Now this is where it gets a bit more interesting. Deb Bootstrap knows, it goes and looks for what's called all of the required packages. So Debian packages are tagged in a particular way, and there's a bunch of packages that are required, and that's basically the the very sort of trim base operating system. And by default, Deb Bootstrap will go and evaluate what all of those are and install those packages. And what we're going to do is coerce that behavior a little bit by excluding some packages that it will find that we're going to say, don't install those. Hello, Sparky Geek, welcome. Yes, so Sparky Geek, who is a friend and ex-colleague who works at Canonical. Yes, Nano Fiend indeed. Trolling a little bit maybe. So these are some bits and pieces that we probably don't need. It's debatable whether we need DM setup or not. I'll exclude it for the time being. But this is internationalization strings for debconf. Debconf is a tool that manages the configuration prompts for Debian packages when they pop up. We're just going to exclude that to save a bit of disk. Distro info, I don't think we're going to need. I've checked it's a front end to some database, and the database we are preserving. DM setup is for logical volume management. You could argue we might want something like that, but I'm going to exclude it for the time being. Eject, this is a curious one. Why eject is still an absolute required package. Eject is responsible for ejecting CDs from optical media drives. It's curious that that is considered a required package in this day and age. Certainly on a Raspberry Pi it seems irrelevant. Info, Debian and Ubuntu have a lot of info pages, which are a bit like man pages. but we don't need the info command. I'm just making an opinionated decision. We'll keep the man around. I'm going to make an argument that netcat is useful but not essential for what we're doing here. Now what we also do is we exclude the Ubuntu minimal package itself. The Ubuntu minimal package basically defines a number of these packages as to be installed. So by excluding this meta package, we're preventing them from being pulled in. Then we have Ubuntu Advantage Tools, which is a whole bunch of sort of value add capabilities from Canonical on Ubuntu. But this comes with some additional services and persistent services and things of that nature. And I'm going to argue that we want to try and keep the footprint as small as possible wherever possible. So we're going to exclude that. And then this was from the Retro OS, and I thought I'd keep it for the lols. We're just not going to bother pulling in Vim Tiny. We'll just go with Nano as our single editor. Foreign means this is a foreign architecture, and we're going to do a second stage in the bootstrapping process, which I'll get to in a moment. And then what we're also going to do is we're going to include some packages in this initial seeding of the base file system. So one of those is Cloud Guest Utils. Now the reason for this is that we're going to be using a facility to grow the file system on first boot. So we'll have a file system just big enough for the bootloader and the firmware and the root file system. But when that card boots for the first time, we want to expand the root file system to the full capacity of the media that we're using. And we'll get to what that utility is called, but that utility has two dependencies that can satisfy it, and one of them will pull in QEMU, the whole hypervisor. Worse still, it's QEMU for x86. So you get a whole bunch of stuff in the Raspberry Pi image that is really of little to no value on a Raspberry Pi. So by using this package instead, we don't get the QEMU hypervisor and all of that x86 stuff dumped on the file system. And then, because I like Nano, we're going to include Nano as our one true editor. And then once those packages have been sucked down, there's then a second stage to the bootstrapping process, which installs and configures each of those packages. So that's sort of like our starting point, and this is where some of the tuning happens early on. So now we're going to look at creating. So I'm going to need to copy some files in from my other project. So let's make a couple of directories here. We're going to need to make boot and root etc. There we go. Oh, and that's wrong. So I've got some remix things. So remix is from my other project. So this is going to be Slim.AI OS, because I always kind of liked AIX back in the day. So I'm reliving some of that moment. Right then, so we're going to copy over a sources list. So this is the what we would use for the apt repository configuration. So I'm going to copy that in from my other directory. So retro home root etc sources app sources. Okay. In fact, so we're going to need to etc apt. So if we just take a look at that, this is sort of ready to be templated. So I just get rid of that there. We've got this wording caps release, and what we're going to do is just do an inline sed replacement on that repository for the release that we're targeting. I'm going to build with Ubuntu 22.04. So let's have a look at Sparky Geeks. Did you consider a one-step sed template destination instead of copy the template and then an in-place sed? I could do that, couldn't I? Yes, that's a good idea. Let's do that. So, well, I'll leave it at the moment because I don't want to introduce new variables, but I understand what you're suggesting, and I think I will change that in due course. So instead of doing this, we can just sed. In fact, let's do it. Let's do sed that and output it to I think that is what you're suggesting, is it not? Okay, so then I think that's correct. Yep, thank you, Sparky Geek. That's a good tip. So we're setting the host name. We're setting up the hosts file. We're just jamming the C language string in there for 0 internationalization. And then here's a couple of things that are interesting. So we're going to disable cron, and that's because all of the services that are installed, all of the packages that are installed in that bootstrapping stage, and in fact what are going to be the following, at least at the moment, well, we'll have to reevaluate this, but everything that's going to be installed, it'll have conditionals at the top of each of their cron tabs to say if systemd exists, don't run this cron tab, because all of these things have systemd timers shipped with them as well. So what we're doing is we're going to disable cron to remove a process from memory and rely on systemd timers instead. And then when I went and looked through those timers, there's some stuff here that reaches out and updates the message of the day information. And again, we're going to disable those to have a few services which don't get enabled from time to time. Well, not services, timers that create jobs from time to time. It's just not important for what we're trying to build here. And then I'm not sure about this, but here's an interesting observation. Quite often when I go looking at things like, you know, Stack Overflow and Q&A places where people are talking about deploying containers into the various cloud providers, they quite often, there's a trend of topics which is, how do I disable unattended updates? How do I disable the apt stuff? Because their new container comes up, they use something like Ansible to go and connect to that container and provision a bunch of stuff, and then apt is locked because there's some unattended process that's running. So what I'm doing here is I'm disabling that stuff so that you don't get those deadlock situations where now this is intended to be a development machine, but I've seen this many times crop up, so we're just going to try and sidestep this issue entirely by not having these things run. This I don't think we're going to need. This is for setting up the VTs, the consoles effectively on the Raspberry, well, on Linux in general, but I don't think we need this for the Raspberry Pi. So again, we're just going to remove it. I'm pretty sure we could get away with it, and this just helps the first boot performance. And once we've done that, we'll then just do some updates and upgrades to make sure we've got all the latest stuff in that initial base file system. And now we come on to this bit here. So there is a meta package in Ubuntu called Ubuntu Standard, and that provides a whole bunch of sort of common user space tools. Let's go and take a look at that. So let's go to SlimDevOps, os, and if I just show Ubuntu standard. So we can see here there's two types of packages. There's depends here. So there's a bunch of stuff here that will get installed, and then recommended packages. And in Ubuntu and Debian, by default, recommended packages get installed as well. So I've gone through this list before and sort of made a determination as to which of these are genuinely useful and which of these are questionable if you're making something that's targeting a small form factor device. So if we go and take a look here, this is what I've decided to whittle this list down to. So I'm saying do the install and do not install any recommended packages when evaluating this list of packages here. So this is where we are saying go and get the tools we need to grow the initial file system. And again, we're just making doubly sure it doesn't go off and try and satisfy a dependency for that other package which is going to bring in QEMU. The DOS file systems is because the Raspberry Pi bootloader sits on a FAT file system, so that's something handy that we need. File I just don't think we can do without. HDPalm, because we're going to be potentially working with SD cards, eMMC, and SATA connected USB drives, for example, this is a useful utility to have on a Raspberry Pi. Hardware stuff, all of this is sensible. Having man, I tried excluding it, it was deeply frustrating, so I've left it in. Some of the newer Raspberry Pis do have some PCI connected devices now, so we'll include the PCI utilities and the IDs. Basic process management stuff, and again for the USB utilities and the USB IDs, and then wget and xz utilities. That's because Raspberry Pi images are often shipped compressed with xz, so that's something that may be useful. But that makes up our base platform, and Sparky Geek has got a question. Yes. Nano Tiny instead of Nano would give you an additional 700k of space. Yes, I'm aware of this. It's just Nano is great. Nano Tiny is a bit like trying to pick your nose whilst wearing mittens. And for the same reason that I've excluded Vim Tiny. So I feel like people that like Vim really want full blooded Vim, not the tiny edition. So, you know, if you find yourself on this system and you really want Vim, then you can install the full version. And I'm not going to hamper Nano by, you know, putting the tiny edition on. It's a good idea, but that 700k, I'm prepared to take that tax. And we could argue that maybe some of these we don't technically need, but this feels like it gives us enough of a sensible system. Things that you don't have that can get frustrating is no bash command line recommendation. So if you're used to having package names autocomplete and things like that, none of that's here. But really, this isn't an OS that we're expecting to have to jump into and manhandle very much. It's really like a deployment target, a build tool, a deployment target, not something that we're going to be working on. So I think that's the first stage. I think we should start by running that and actually build out the initial file system. So I'll just save what we've got there. Down here at the end, we've only got that stage 1 highlighted. This here just builds out our cache directories for the project. And I'm not going to use that because I have specified that ARM64 is the target. So if we just look at this, we'll come back to this later, hopefully. But we're going to build with the current LTS version of Ubuntu, so that's 2204, codenamed Jammy. We're going to calculate a date stamp for our image, so like a revision effectively of the build. That's just for my sanity, apart from anything. And then for the time being, we are going to hard code our username and password. And in the future, I may replace this with clouding it, or simply replace it with a if you connect, you have to change your password type policy. But for the moment, for simples, we're just going to hard code things, but we're not actually going to call any user creation at the moment. This is just going to build the OS file system, the very first run of this. So hopefully, did I save that? Yes, hopefully this will work. So we will run image. Let's actually pass in the thing and say ARM64, even though I shouldn't need to do that. I just want to see if that works. And there we go. So that piece there is making sure the host requirements have been satisfied. And this is the bootstrapping process running now. So you'll see that ran quite fast, that initial piece, because I've already pre-cached these packages that the bootstrapping stage uses. So now it's on to the second stage here. It's evaluated that package list. So now it's installing each of those packages. I'm just looking carefully to make sure that there's nothing unexpected in there. Now it's configuring them, so each of those packages will have some post configuration steps that need to be done. And then there may be some additional setup that needs to be done. So for each of those, it's going to do that. And we'll take a look at that sort of file system once it's built. So whilst it's building, let's just head back over here. So we're going to, after this stage is completed, we're going to move on to this. And like I say, for the moment, I thought we'd go with Docker. So our second stage looks like this. So B and R are just variables that I use as placeholders for the boot partition or the boot file system and the root file system, because the Raspberry Pi will need both. And then I sync from the previous stage to the current stage. So that means that I can iterate on these. So if this Docker stage I need to iterate on, I can just run this, and what it does is it grabs the first stage, syncs it over, and then builds again on top of that clean sort of cached stage. And then I have this little conditional here to say if include Docker, because what I'm thinking is maybe this stage 2, maybe we call that container runtime or something in the future, and we can have a couple of different conditionals in here for, say, podman or containerd, or maybe aspirationally thinking some kind of Kate's environment. So what I've got here is I've got another project that I work on called debget, and in fact yesterday on my own channel I released debget 0.3.0, and debget is a bit of software that enables you to install packages on Ubuntu that are from outside of the Ubuntu repositories. So instead of apt-get, you can say debget, but you can say debget install, something that lives beyond the Ubuntu package repositories and archives. And one of the things that I've got in there is a mechanism for installing Docker, the Docker engine. And I'm considering using debget, but actually Docker engine is actually installed via a third-party apt repository. So I may sidestep putting debget into the system and just do the necessary steps here to enable the Docker repository and install Docker engine that way. Now, having never installed Docker Engine on an ARM platform before, I don't actually know if their apt their third party, or in their case Docker's apt repository, has builds of Docker for ARM 32-bit and ARM 64-bit. So we're going to find out the hard way. And if they don't, then I'll have to have a hard think about how we overcome that issue. So let's see how our file system construction is going. So it's doing the setup. I think it's quite near the end. Oh, in fact, there it is. It's just finished. Right then, so let's take a look at what we've built there. So I've got a directory called builds. We're building for ARM 64, and our OS is going to be called this. So here we can see there's our cache directory, and these are all of those packages that we pulled in that are actually used to compose the initial root file system. And then if we look at one root, this is the file system that we currently have. So this is an Ubuntu user space file system with no kernel, effectively. So when I get to creating optimized base images, we will use much of the same techniques to sort of create the initial root file system, but we can be a lot more opinionated in what we exclude or include in that to, minimize it. And the challenge will be, is it even possible to make a base image derived from Ubuntu that's smaller and more optimized than what Canonical provide? And I think it would be arrogant to assume that that's going to be trivial, but we'll have a go and see what we learn in the process. So there's our initial file system. So this is all good. We can't boot any of that on a Raspberry Pi at the moment, so let's go and grab some extra stuff. We'll go and have a quick read of how we enable the Docker Community Engine third-party repository, and we'll have a go at installing that here. So it's going to be, we're going to do this inside the container. We're going to do apt add repository. It's not going to be that, but this gives you an idea of how it will work. In fact, is it even going to be that, or is it just going to be thump a line out? Yeah, there may be some advantage to using debget, actually. I can think of why debget's not going to work. I tell you what, let's try it. So we're going to satisfy some of debget's requirements. We're going to then use debget to install itself. Make sure that that's done. So that is installing debget. And that will pull in the unattended upgrades feature, which we're going to disable for the reasons that I discussed earlier. And then we'll try and do this. This Copilot thing is really working. Oh wow, check this out. Look at that. That's Copilot just suggested the comment and the line. And what's amazing is it knew about my stuff. So that's exactly what we're going to do. I've no idea. I think this is going to work but complain, because I'm aware of something that's not right in debget, but we're going to actually try that. Oh man, I'm really digging this Copilot thing. I've been trying it for about a couple of weeks now, and however long it is since it was officially released, and I'm quite impressed. So that's the stage we're going to run. So we will just rerun our build process again and see how it goes. Okay, so this is pulling in the debget requirements, installing debget itself, and here, so this is debget being installed, and I'm expecting to see some complaint. This is why I'm thinking, because I need to put software properties common on anyway, and that's going to pull in most of this stuff. So yeah, I'll have to have a think about that. Yeah, Sparky Geek, I continue to be impressed by Copilot. It should I should stop being surprised by how good it is, I suppose, but I think it's terrific. Right then, we're just waiting for these installs to complete, and come on, let's see if the Docker engine bit's going to work. So here's the Docker CE bit running here. Oh, look, it seemed to do the right thing. It's put ARM64 in the architecture of the sources file, so that's encouraging. Reading the package list. Let's see how it goes. Okay. Well, okay. I do like it when you get some payback from another project that you work on. You're trying to do something else, so I'm very happy with. Sparky Geek is asking, how does it know where the public key is for that signed archive? So what debget has is for each package that it knows about, it knows what the repository definition is and where the appropriate signing key is published by the vendor or project. So it automates the adding the signing key and putting it in the appropriate spot and all of that stuff. So it kind of how adding a PPA works. Well, okay, that seems to have worked. We now have Docker inside the container, and it's enabled the service files for it, the systemd units rather. So I think with that we can move on to the next steps. Now this is where we may need to do some work, because I suspect there's stuff in here that I haven't got the necessary configs for. So let's go and take a look at that. Let's have a look. So yeah, so we need to grab the FS tab because I don't have that yet. So let's go and copy that one over from my other project, because this will be the same. That just can go there, and then we'll open that up so we can just explain very briefly what a Raspberry Pi file system looks like. So there's two partitions: writable, which is a label, and the reason it's labeled is so you can put these images on SD cards, eMMC, SATA connected USB drives, for example, or thumbsticks, and it will always boot off the right places based on these labels. So this is an extended 4 file system, and we've got this tag on it here to instruct systemd to call the appropriate grow file system tooling, which we've got integrated into the image. And then this boot firmware partition, as I say, is a fat partition, and that's where the Raspberry Pi bootloader, symlinks to the kernels, and initial RAM disk and stuff like that are going to live. So we don't need to make any changes there. That's well understood. Now what we're also going to do is we're going to poke into the initial RAM disk configuration, some optimizations to enable ZSwap, and this we'll have to take a look at this. I'm interested to see what we do, what happens if we put like an OS on the Pi under memory pressure, running a bunch of containers and get into a swapping situation. But if we do, this is the best outcome of having a Raspberry Pi swap to an SD card or a USB drive or something like that, because you get decent compression there for less I/O, and also because it's the write operations and the read operations to the storage which are actually the bottleneck, the compression helps here because it doesn't tax the CPU. So it's the best thing we can do. And then what we need to do here is copy over some of these systemd units to actually initialize that swap file, so we don't create a swap partition, we have it stand up a swap file. So we'll do the same thing here. We will make these directories for our configuration here. We will copy in user lib systemd system mk swap service to root user lib systemd system, and similarly, what's the other one called, swap file. So these run on first boot. We'll just take a look at both of those. So this says that if a swap file doesn't exist, run these commands to create the swap file. So that's as simple as that. And then this is what's actually responsible for using that file as swap. So that's all fine. Now then, this is where it gets interesting. So these are the packages that define what's required for the kernel on a Raspberry Pi. Now I have tuned this to some extent in that I've elected to not install the kernel headers because generally speaking you shouldn't need them, but if you do ever need them, it's a single package. But for space saving purposes, we will not install them by default. But then there's a couple of things here, and I'm going to not install RaspberryConfig. So that installs a bunch of extra stuff, and more importantly, this package is purely imported from Debian. So consequently, about 80% of what this is supposed to do just simply makes no sense on Ubuntu. It just does not work, and it's usually used by people that are changing HDMI video settings, and we're going to keep this down as a console headless OS. So I'm going to remove that from the equation completely. And then this RPi EEPROM utility, we could argue, is not always necessary. It only makes sense on Ubuntu, on a Raspberry Pi 4, and it's a means to update the firmware. I think I'm going to keep it around because even whilst I've been working on my emulator stuff, I have booted Raspberry Pi 4s that I've not touched for a while, and they have got old version of the firmware, and it's actually dead handy just to be able to update the firmware. So I think I'm going to leave that on here. All of the rest of this is absolutely essential for sort of the smooth running. So this is the kernel. We won't need this anymore because we're not going to install RaspberryConfig, and this has a bunch of stuff inside it. A couple of things which are things like gschema overrides for the desktop, which obviously doesn't apply here, but they're very small text files. But what it does give us is some UDEV rules for some of the Raspberry Pi devices that we need to be able to access, and sets the permissions accordingly that, you know, regular user accounts are able to access those devices in a sensible way. Then we just have a whole bunch of assumed knowledge, and this is stuff you just know when you work with the Raspberry Pi about how to copy firmware and device trees around to the appropriate places on the boot partitions. So that's what's going on here. And then some symlinking, or copying in this case. Yes, they're not symlink, they're copied because they can't symlink across that file system boundary. It doesn't like it on a fat partition. So copying the kernel that we've just installed and the initial RAM disk into the boot file system. And this was very specific to what I was doing with my handheld retro stuff, and we definitely don't want to be doing. So we will not hide those kernel messages. I think that would be useful to see. So we've copied these over. We've copied the file system over. So let's just look ahead at the configuration. Okay. So this is copying in the configuration files. I'm just having a little think. We certainly don't need much of this. That's fine. We don't need this piece here at all. What we do is that. We don't have that file yet. And again, this is because my retro gaming thing has different cases that it can support, and we don't need to worry about that here. We do need this ARM specific bit. And this is then creating the user account and what have you. So, and then that puts that service in to regenerate the SSH keys, which we'll need initially, but could be removed if we elect to use Cloud Init at some future date. And then we don't need to do this because, in fact, maybe if we just I will review this. For the moment, I'm going to... So I disabled these again on my one because I wanted to minimize the number of things that were being executed, and I elected to put a static message of the day in. So we could potentially do that. I'll just comment that out for now because it's not on the critical path. But we should go and copy these, get copies of the README for the bootloader stuff and the configuration for the bootloader and the command line for the Linux kernel parameters. So let's go and copy some of those bits over. And make sure, and they'll need adapting because these are going to be, in fact, yeah, I'll copy them over for the time being, but we will change them in due course. So that can go there. Command line can go there, and so can config.txt. But at the moment, these files that I'm copying over from my other project are very much geared towards bringing up a graphical environment. And we obviously don't need a bunch of that stuff. So if we just take a look at those very quickly, the README just explains what's in the boot partition. And if we add Cloud Init, we can add some additional documentation there. But if we just look at the command line, that's the simplest one to clean up and make sensible. So we've got the ZSwap enablement here. We want to keep all of that. We want to return that to TTY1. There are reasons why I had to move it to a different TTY. We want all of this. We will then remove these lines because we want to see all of this stuff. Although we do not want Plymouth running under any circumstances. Console blank. We don't need that, and we definitely don't want that. So that's probably sensible for what we're looking for here. And we have quiet. I'm going to suggest we probably don't even want that. If I just go and very quickly look at another project of mine, I made a copy of the bootloader configurations from the different versions of Ubuntu. So let's just take a little look at those because that might give me some advice on where to go. Oh goodness. Hello. I don't like the news popping up. That's new. Oh. Ubuntu Pi image, there we go. So in here, which is looking a little bit small, let's just do that. If we take a look here. Yeah, so it does have quiet and splash. I'm going to remove the quiet. I think I'd like to see what's going on. And we have that configuration. So I think what we'll do is take this one and we'll copy that over this file here, config.txt. So this is going to be almost identical, but we'll do this and then we will replace this piece here with this stub, which I now am choosing to make a comment. So we'll do that, and then what this will do is have, so I'm not going to get into this now, but we can in a subsequent stream look at how to tune this stuff so that again we don't enable facilities of the Raspberry Pi SoC that we simply don't need. I think you could make an argument for saying we don't need Bluetooth and we could just disable Bluetooth outright at sort of a hardware level, and then that stuff we don't need in the host OS, and we can also disable there. And the reason why that's important is actually bringing up the Bluetooth adapter on a Raspberry Pi is extremely slow and does impact the boot performance significantly by several seconds. So that's all stuff that we can look at in a future stream. All of this is sensible, though. We could argue that maybe we don't need audio. In fact, that's a question for anyone that is running containers on a Raspberry Pi. Are you running any containers like Volumio? I don't know if Volumio is available in a Docker container, where you would want audio on the actual device, you know, to pass through audio from a container to the host. Having never done it, I don't know. So if anyone's doing stuff like that, that would be good to know. This we probably don't need. So I think these are things we can comment out, but we'll just leave them for the moment. So what we're doing here is we've got this little ARM64 tweak. So this again is doing a SED replacement, and we'll just change this here, this stub, for the commented version. It seemed to me that actually putting in a replacement, a string replacement should be more clear what it is, and commented seems sensible. Okay, so if we look at this, this is creating our initial user account. We could do better here. We may use Cloud Init, we may not, I haven't decided yet. And then this we need. So this is a service. In fact, this is something I was thinking about as well. I may drop OpenSSH because we could use Dropbear, which is a much more memory efficient SSH server and has a nice feature where we can remove all of the host keys from Dropbear and tell Dropbear that the very first time it gets connected to, and there are no host keys, to generate them on that occasion. And the reason that that's advantageous on a Raspberry Pi, particularly the lower power ones, is that quite often in the early boot stage where SSH keys would get generated, there isn't enough entropy in the system for the host keys to actually generate in a timely fashion, and again it can hold up that initial boot process by some considerable time. So what I may do is switch to Dropbear, because the first time you connect you will have got much later into the process, and there should be a good entropy pool on the system in order to satisfy that key generation. So I'll leave, in fact I'll I'll leave this. What we'll do is I'm going to stream again later. This is part 1 of 2 that I'm doing today. I think on this evening stream, my time, I'm going to look at replacing this with Dropbear. But for the time being, we will copy over the configuration for hoovering up the, or rather regenerating the SSH keys on start. Shouldn't be a problem on my dev machine here because it's a Raspberry Pi 4, so that it should be fine. Right then, let's grab that then. Let's see, it is copy that in there, and we'll just take a little look at that very quickly. So again, this is, you know, if the host one of the keys that are generated by this process do not exist, then run the process to generate those keys and run it before SSH has been brought up. It's, you know, a simple unit but quite elegant. And I talked about this. We're just going to leave that disabled for the time being. So I think that configuration step should work as well. So I usually run the kernel install and configuration steps together. So let's go and do that thing. Let's go and run this again and run the kernel and configuration steps. There we go. So this shouldn't take too long. We've actually trimmed down what this does now. So there we can see a bunch of packages that represent the kernel requirements for the Pi. Interesting. I've just seen the wireless regulation database get pulled in there. Yeah, interesting. Okay. I still haven't figured out what happens when you don't actually configure the wireless regulation authority for your chipset, which it defaults to. This was why I was considering not including this, because it does come with a service. So yeah, we'll get on to like optimizing the bootloader later. So I think the second part of this stream later today, I'll look at replacing SSH, OpenSSH with Dropbear, and taking another look at whether we really want the EEPROM updater on this. You could argue that once you've got a Raspberry Pi 4 in service, though, you probably do want to talk. I mean, you could install it. You could install it. Yeah, I think we'll say we don't. We're not going to install that by default for optimization's sake. So yeah, we'll look at bootloader and some more memory and service tuning. But then what we'll also do later is, at the moment, I just want to get this to a point where we can make an image and boot it and prove that it works. And that would be like, okay, we have an operating system. That's sort of like milestone 1. I think the other thing to look at in the next stream will be, well, let's take an Ubuntu server image for the Raspberry Pi, the same architecture, and compare their running footprints. Have I actually moved the needle? Is any of this helpful? Is any of this necessary? And sort of get a feel for whether we're in diminishing returns or not. You know, I'm quite happy to, you know, find that there is no significant advantage, but I'd like to think that there is going to be some payback from doing this. So we're not far off from this step completing, and I think Dropbear I mean, there's considerable amount of memory to be saved there. So then that's the funky stuff that copies the bootloader around. Our user's been created. The SSH stuff has been done. Okay, so let's go here. We'll disable these 2 steps. We'll run the clean an image steps very quickly. We'll just take a look at what those do. These are very simple. Well, this one's simple. This is the clean step. So make sure all of the cruft that could have been left behind has been removed. We'll have to add something for drop bear in there, I can see. So that's all just cleaning up stuff. This we don't need. That's a hangover from my Retro OS thingy, which uses a different networking stack. And then this step here, because at this point we've created file systems for the boot file system and the root file system that are, you know, being built by a container. But those file systems now need to go into an image that we can put on an SD card. So what we're doing here is calculating what the size of that image needs to be. So we look at the size of the root file system that we've created, work out what 5% of that is. This is our margin. And then work out what the size of the image is going to be based on the size of the boot partition, the size of the root partition, plus 5%. And that, I recently came up with this, I'm going to call it an equation, so to sound clever, a few days ago. And this is by far the most accurate one that I've come up with in the last 7 years. And it is always exactly 5% bigger than is required, and which is just what you want. And then we create a sparse file that is that size, and then we treat it like a disk at that point, and we create partitions, and we make file systems, and we then copy those 2 file systems. An empty file, yes, indeed. It's exactly what it is. It's quite clever. The other day on my system at home, I got the sums wrong, and I was able to create a 2.6 petabyte sparse file on my computer. I can assure you, I do not have 2.6 petabytes of disk laying around, but it's quite fun what you can do with sparse files. So yeah, we create that sparse file, and then we copy our root and boot file systems into the partitions that we make, and we're done. We're not going to do this compression step because it's not necessary, and it burns a bit of time because it's quite an expensive operation. So that's what we're going to do. It's going to clean up our file systems and then turn those file systems into images. So let's just run this step now. So it's bringing over the cache. And there we go. It's now syncing over the root file system, and we're done. There's our image. 2.5 gigabytes. Huh. That's not that small, I would say. That suggests there is room for improvement here. I mean, 2.5 gig. Huh. Way more than I was expecting. I thought we were going to get closer to 2 gig. But that is the size of the OS. So at least, let's go and have a look. Let's go and have a look at something. So let's do this. Oops. In the builds directory, I should have, there it is. There's my image there. So let's open this in the image mounter. And I can see here, so this is just a sort of hang on a minute. Oh, because I'm building an ARM64 image. Okay, that's fine. I was going to say there's not enough device trees in here, but that's fine. This is only going to work on those devices that can boot 64-bit. So we will then take a little look here and make sure our command line.txt file is correctly formed. And indeed, that looks fine. And then let's go and check that the config.txt is correctly formed, because we should see that didn't work. So that bit didn't work. So bother. I'll go and manually paste that in by hand. But I will need to fix that in due course. So let's just go and grab the 2 lines that we need for that piece and drop those into the right spot. I wonder why that didn't work. Is that because it considers that special character? I'll have to research that. So, oh, did I close it? Oh no, I opened it in this editor. That's right. So let's just put those 2. Why did that not copy over? Come on, brain. This is so it instructs the bootloader to... What? Why can't I edit this? Oh. I'm trying to edit it on a read-only. No, it shouldn't be read-only. It is read-only. Why? Okay. Well, let's change this to that. And just for quick sake, and change that to that. And then go back to here and rerun the config and clean steps, because I think that was in the config step. I'm guessing that it's the comment in that string that it doesn't like. Okay. Unless img arch is just not... No, we know that's set correctly. Okay, let's just quickly rebuild those stages. I need to go from config, don't I? Config. Let's rebuild from there then. So that's going to go back a few levels. So it's doing the config step now. There we go. Hang on. Config's after the kernel, so that should have been quick. Okay, and we can actually check that this is correct very quickly by looking at builds. This is ARM64 SlimDevOps. It's 2204, and it's going to be... Oh, hang on a minute. I've done a bad. I've done a bad. How have I missed there? Got this word remix. So, okay, it's not catastrophic, but that will need fixing. So we've now got this. And we should have a 5 in there, and a boot, and a config. Okay, and it's still not replaced it. Why not? This is working fine in my other thing. What am I doing wrong here? We will leave that for the moment. I'll have to fix that later. That's busted. Why is this not doing the right thing? Well, that's curious, isn't it? Let's just check that we're catching this correctly. Not Prince, not Python. Let's just go and rerun that and see what's going on. I should see. There it is. It's finding it. Okay. So the conditional's working. So the question is, why is this not working? Well, it used to be just that. Oh. Yeah. Well, I'm pretty sure this isn't going to change anything, but let's do that, rebuild, and then see what we get. What? Well, this is frustrating. This is a bit of code that's working somewhere else and not working here. Okay. We're gonna, in the interest of time, we're just gonna fudge this. So let's do this. Let's go and edit that file. In fact, we should be able to do that. Just replace this bit here with the correct words. Save that. Insufficient permissions. Okay, so I do need to. Terminal that I'm not used to using. Behaves a bit differently. Okay, so what we'll do is, having just hand patched that, we'll now just run the image step. And that should give us something that works. So I'm just going to turn my Raspberry Pi off in front of me a second here. I'm going to pull this out. So I've just grabbed, oh, that's the wrong thing entirely. I've just grabbed the SD card out. And I'm going to put that in this card writer that I have here, the right way up and everything. So we're going to write out our image to that SD card. Did that appear on the right screen? There we go. So we're going to choose our operating system, which is going to be our custom, this image here. Choose the storage, which is our card in the card reader. Do you want to continue? Yes, I do. Do these things. So that hopefully is an image that's going to boot and function correctly. So we'll just wait a mini moment, hope that that ARM64 configuration is correct. In fact, we know it is because we edited it. So if we do that, we know that that's got the right bit in there. I'm going to have to check why that is not working. So it's doing the verification. This takes just a moment. I recently invested in a decent performing card reader writer so that these things don't take too long. Right then, let's take that. And what we have now is this card, which is going in this machine here. Hopefully, if I switch to this view and we turn the Raspberry Pi on, we should see at least the thing boot. Well, that means the bootloader has at least been found, which is sort of step one in the process. So the next thing is, does it find a kernel? Does that kernel start to load and boot? And indeed, there it is. Curious that those Raspberry Pi logos are there. I didn't realise that that existed in the Ubuntu version of the Pi kernels. How interesting. Okay. And there we go. So there's our OS there. And if I log in as SlimDevOps, no, not that keyboard. Let's try this again. I've got another keyboard here, which is connected to the Pi. So we'll just very quickly, little wireless keyboard, the dongle's in the back of that there. So let's try logging in. I can't do anything about the font size, but I think I set up the user to be SlimDevOps, and the password is test, and we're in. There we go. So what we'll do now is, as that's working, we'll come back here. We'll actually try and SSH into that device. So we'll use sudo netdiscover, because I've no idea what the IP address of this is. That should find it. Oh, it hasn't. Oh, I wonder if that's because we don't have a default network configuration. Okay, so that could be a thing I need to fix later. So we'll come back and do that here. Do it this way. So I think if I do IPADDR, indeed, it hasn't got a network configuration to automatically bring up the Ethernet device. So we'll fix that with a net plan configuration a little bit later, because I think it's sensible to continue to use netplan. But we can see that the Docker interface is there, so that's terrific. And if we just have a look at the process tree, what are we running? Not very much. This is good. So we're running dbus. What's this? Network D dispatcher, fine. Syslog stuff, login D, and there's container D from Docker. There's Docker D, and here's the Bluetooth stuff. And again, if we just do a quick system D, oopsie, hello. I don't know why this device doesn't like my power supply, but I need to figure that out. So system D, analyze time. What have I spelt wrong there? This is so small. I know this is small and I can't do much about it, I'm afraid. Oh, with a Z. Okay, and so that came up after 17 seconds, the graphical target, which we don't care about. We could probably do better there to maybe get rid of the graphical target entirely, because it's never something we want to achieve with this operating system. And if we just look at blame, we can see some of the impact of like the Bluetooth stuff, which is why, you know, I think maybe we'll drop this. Up the top here, so the SSH keys took a while to regenerate, that's reasonable. But here's the HCI UART, and that's 7.1 seconds. Docker taking 4, AppArmor 3, but these are in parallel, so it's only when you get really long running ones that it actually pushes the whole thing out. So we should be able to reboot and see a much shorter reboot, startup time. So let's do that. Interesting. I didn't know that those Pi logos were going to be there. I'm going to have a little think about that. That's an interesting discovery for me personally. I was sure that Canonical patched out all of those logos in the Ubuntu kernels, but maybe as the patch set for the Raspberry Pi enablement, that's kind of like a baked-in requirement. So this is doing a decent job. There's definitely some things we can tweak here. So well, we're making good progress here. So let's just do a few things. Let's look at free. So we can see the swap is definitely enabled. Oh, we're using 153 megs of RAM by default. This is good. I know things. I think I can tell that we're already winning at this point. We've brought back quite a considerable chunk of memory with these changes, but later on we'll actually go and compare that. And then if we just do looking at disk free, we can see that the file system resizing has worked as well. That it expanded to the full size of the card. So I'm pretty happy with how this is looking. I think if we just do a quick systemd analyze time on that one, because this wouldn't have had to do the file system, it's still 13 seconds. So there's gains to be had here, because I've got my retro thing down to about 8, and I'm sure we can do something similar with this. But this is good. So other than a couple of little quirks to fix in the build environment, I think we're in a good spot. So let's just come back to here. That was my code. So let's bring up VS Code. So I think we're in a good place. We'll make some notes about what to look at next, because we will do a part 2. So let's do a quick and dirty to do. We'll do a net plan, ETH0 DHCP. I think that's sensible. We'll look at fix the cache paths, because I've made a boo-boo. Remove remix. Replace OpenSSH. There we go. Even the comments. Look at this. It's making a guess at what I might want to do next. It's not that, as it happens, but I do like this Copilot suggesting comments. It's brilliant. Okay, so replacing OpenSSH and this. Let's look at bootloader. Loader optimizations. Disable Bluetooth. Wi-Fi perhaps, and what else? Audio, GPU, RAM. So we'll look at a bunch of those things and we'll see what we can buy back. So I think that's probably a good place to start with that. Okay, there we go. So that's what we'll be looking at later on. So for those of you that are stuck with me there, we've got, I think, 9/10 of the way there in that first thing. We did actually get something that booted, and my initial guess is I think that we're already using about 20 megabytes less RAM in this OS than the Ubuntu server image for the same hardware. But we will actually do not an in-depth assessment, but we'll do a quick comparison later to see if that's the case. I think 20 megabytes is worth it. Is worth it. Hey, Big Pod, did you join at the end? Hello, Big Pod. Big Pod is my colleague, Primosh. Yes, unfortunately, you're joining at the end, but that was part one of a two-parter. So you can watch the VOD, see what I did, and later on, I'm going to do the next bit, which is let's see if we can improve on the situation a bit more. And Primosh, if you want to hop into the stream later, I've even created these so that there's a spot there just for you, so you know how to join me if you're interested in doing that later. You'd be more than welcome to come and pick my brains and make sure that I'm doing the right thing, particularly because I'm going to get to the point where I want to do stuff with Docker. But I do have, in fact, is it still up and running? I do have an operating system. If I just, this is very difficult to see because it is the console of the Raspberry Pi. I can't SSH into it because I have no networking at the moment. But if I do an IP ADDR, you'll see there's the Docker interface. So that's being provisioned correctly, automatically. And if we do ps minus EFH, oh gosh, if I could just see the screen, that would help. Gosh, right, there we go. No. There we go. You'll notice that we've got Dockerd and Containerd are running part of the default system. So we're a good way there. And I think it's smaller. I think it's smaller already, and we'll see what we can do to improve on that in the future. So Primosh says, I'm just bringing the memo from you so you can do from the you can do this department. Oh, very good, thank you. So I was making the joke that these challenges are from the how hard can it be department. So Primosh is telling me that that this is from the you can do this department. Yeah, this bit we've got. So later we'll do some more optimization, and then I think in some subsequent streams next week we'll try and do the same process for base images and try and make some smaller Ubuntu base images, and then we'll see what kind of density of containers we can get on a Raspberry Pi using our sort of optimized OS and base images. That's sort of like the next step. And then of course, something I should do is I should install Docker Slim by default in this container. That's I'll add that to my to-do list. That's something we'll do later. We'll install Docker Slim. Because obviously I want to make smaller, faster, better containers. Hey Tommy, how you doing? Yeah, I mean, I guess this would be a breeze with Nix OS, right, Tommy? You're probably wondering why I've gone to all of this effort. Could you not compose this in a matter of moments with Nix? Right then. So I think I'm going to call it there. Thank you very much to everyone that stopped by. I'm just seeing if any of our friends from Slim.AI are streaming. They are not. I wonder if there's anyone interesting doing stuff. Yeah. Okay. I'm gonna call it there. There's none of our friends currently streaming. So thank you all for joining me. I'm going to be back here in 7 hours exactly to do part 2, and we're going to run through some further optimizations. If you're available, I'd love to have you here to join me to help. It's going to get harder and more complicated as we go. And if not, then maybe you'll be able to join one of the earlier streams I do next week, where we'll look at some of the further optimizations of the containers themselves on this. We'll actually get to, running some containers on this thing and seeing how it forms. So thank you all very much, and I look forward to seeing you a bit later, if not sooner. Bye bye for now. I need to find the right buttons.